Let's discuss norms today. So the key idea of norms is to associate a number with vectors. So norms are basically to measure lengths of vectors or matrices or tensors or something like that. So we'll be dealing with norms of um, vectors and matrices in this course. So the very basic norm is actually something which we are all familiar with, which is known as the Euclidean norm. So given a vector z, the Euclidean norm is defined, the simplest Euclidean norm is defined by set transpose z, which is actually the sum of all the squares of all the components of the vector, zi squared, which is the basic norm which we have. And there are other variations of Euclidean norm, where rather than just taking the squares of individual components, we also have a weighting factor to it. So this is actually termed as Z2. Squared. In fact, this is not the norm. This is actually the square of the norm. Okay, and the square root of this is actually the norm. Okay? And there are another form of Euclidean norm is this, where we have all the components of a vector ai zi squared. What I mean is we have z vector as z1, z1, z2, etc. Zn. This is the vector, and this is one of the examples of a norm. But a more systematic way of defining a norm is, which is what we normally use, definition of a norm. For norm. So in this, what we do is a function. Okay, let V be a vector space over a field F, where it can be real or complex. Then a function, normally define vector norms as double bus, which is a function which takes a vector in this vector field to the real line. To be more specific, it's a positive real line, including 0, is a vector norm. It has, if it satisfies, if for all x, y belonging to V, it satisfies these properties. So this is one. The first property is called positivity property. That is, the norm of x for any x belonging to this vector space should be greater than or equal to 0. There's a property which is known as 1a, which forms like a sub-property of this main property, which is known as positivity. So the first property is called non-negativity. Non-negativity. The second property is called positivity, which means that the norm of a vector is equal to 0 if and only if x is equal to 0. For any other vector which is not 0, it will have a positive norm. This is something which is known as positivity. The second property is something which is known as homogeneity. So if we scale this vector by some scalar, where C belongs to the field F, right? Here, the new norm, the scale vector, is modulus of C times norm of X for all C belonging to F and X belonging to V. So this is known as the homogeneity property. And third property, which is mostly most of the cases, the first was property one A and 2 was easier to show. This is a bit more involved property, which is called the triangle inequality. So you have two vectors x and y, which belongs to the vector space V. Then it has to satisfy. And then if we have a norm defined on the vector space, then it has to satisfy the norm of x plus y is less than or equal to the norm of x plus norm of y. The individual norms is always greater than the norm of the sum. This is known as triangle inequality. If a function satisfies all these properties, then it's called a norm. Okay. And a few more things which we have to notice. If 1a is not satisfied, then it is called a semi-norm. Okay. That means there exists some x in the vector space such that even if you take the norm, the value of the norm is non-zero. Even for even if the vector is not zero, it has a non-zero. It has zero value. Right. Such norms are called semi-norms. So it doesn't have all the properties of norm, but it can be treated as a semi-norm. And if 3 is not satisfied, 1 and 2 are satisfied, including 1a, but 3 is not satisfied, it is called free norm. I mean, the one way to remember this is all the pre properties are satisfied, with the last post property is not satisfied. So it is called as a semi-norm. So this is how we define a norm. Okay. So one of the interesting properties, we'll look at one lemma here. In like this lemma, and let's try to prove this. This lemma states if we have a norm defined, if this function is a vector norm, then we have already seen that it satisfies triangle inequality, but that's for the sum. What about the difference? Okay. But there's slight difference here. Okay, what about this? This lemma is actually about the difference of. What about this norm? The difference between them. In fact, it turns out that this is actually lower bounded by the individual differences. The modulus for all x comma y, which belongs to this vector space. So proving this is very simple. Proof. So the idea is use triangle inequality. The key aspect is to use triangle inequality. So we have to find the norm of x minus y, right? X minus y, the difference. But we just do some rearrangements and express. Let's look at y for example. Y can be expressed as x plus y minus x. Okay. So we'll group these both of them together. So this will group as one vector, this will group as another vector. Then apply triangle inequality. What is the norm of y? So this means norm of y is equal to norm of x plus y minus x. We'll group this together. By triangle inequality, this is less than or equal to norm of x, norm of x is norm of y minus x. So what does this mean? This means norm of y minus norm of x is less than or equal to norm of y minus x. Okay. You've seen this part. So now let's take x equal to y plus x. Sorry, y plus x minus y. Now let's find norm of y. It's the same similar fashion, which will be norm of y plus x minus y is less than or equal to norm of y plus norm of x minus y implies norm of x minus norm of y is less than or equal to norm of x minus y. Right? So if we look at the left side, right hand side, like this and this, let's call this I. So one, okay, let's call this 1 and 2. Both these are same, right? Why? Because of homogeneity. You can take a constant outside, so both of them are same, which means norm of x minus norm of y is less than or equal to norm of x minus y. Similarly, norm of y minus norm of x less than or equal to norm of x minus y. So how will you make sure that both of them holds? This is something we're seeing like x is less than epsilon minus s is less than epsilon. What does this mean? This means modulus of x is less than epsilon. Something like this. If you have positive value. So we're combining both of them, we'll get modulus of, sorry, is less than or equal to norm of x. So this is how we prove this lemma. So we have already have the triangle inequality for the sum of two vectors. It is upper bounded by the individual norms. The norm of the sum of two vectors is upper bounded by the individual norms, and the difference is lower bounded by the individual differences. Okay, and let's end this discussion.